I have done a video explicitly on this study, but since you are so intent on me responding directly to you, here goes again. This study studied quantum tunneling. Quantum tunneling is what happens when the wave function of a particle extends through a solid surface. The particle is that wave function. A wave function describes whether a particle might interact with another particle somewhere in space. So if the wave function has a high probability on one side of a barrier and a low probability on the other side of a barrier, it might interact on one side and then the other side, but the wave doesn't have to move to do so. Nothing has moved faster than light. It's just it has interacted on one side of a barrier and then interacted on the other side. That's what we call quantum tunneling. And if you had read that paper, they had an entire section discussing just that. This is not a paper about breaking relativity. In fact, they specifically said they hard-coded the rules of relativity into their observation. It's a paper about whether or not you could have an effect that appears to be superluminal by having a particle that interacts on one side of a barrier and then interacts on another. Quantum tunneling, again, doesn't really involve moving. And yes, you can have that effect, but the problem is, as you get a wider and wider barrier, the chances of that quantum tunneling effect get lower and lower and lower. That's why they said you couldn't actually send a signal faster than light, because the flux is so low. Meaning if you want something to actually transmit at that speed, if you want to actually interact faster than light, you still have to travel slower than the speed of light because of relativity. They said all of this in this study, which you keep citing as proof that relativity can be broken. So yes, again, same answer that I said the first time. No, this does not prove that we can move faster than light. It doesn't matter how many times you repeat it.